Okay, now I'm going to show how to do exactly the same problem, but this time using vector loops. Alright, when you're using vector loops, you do the same thing. You count the degree of freedom. Everything is exactly the same to determine whether or not you need to do a free body diagram and whether it's a time spanner. All of those things still apply. Now that you've decided that all it is a constraint problem where you're relating one velocity to another velocity, you decide, do you want to use special points or vector loops? What you'll find most likely is that, what I find is that vector loops are by far the easier thing to do as long as you use Mathematica and if you can find the loop that you're going to write. Okay, so the purpose of so what I mean by finding the loop is you want to be able to walk around the mechanism that you have, starting anywhere you want, any point on the mechanism. Actually, it doesn't have to be on the mechanism. Start at some point, walk around, doesn't matter if it's clockwise, counterclockwise, it doesn't matter. Just walk from the point you start at all the way around, okay? And as we do more and more problems, I'll show you some stupid things not to do, okay? Basically, you don't back up, you just keep going forward, push on, push on, push on, and you come back to where you started. Okay, so to do this one, I'm going to start at, I'll put it in red, I'm going to start at point A, right, that'll be my starting point. I'm going to go to B, then I'm going to walk to C, and then I'm going to walk, and then I'm going to walk back to A. So from C, I'm going to go back to A. Now, one of the things you have to be careful of is to make sure you know all of the things that are changing. And if they're changing, definitely, for sure, always define a variable to identify how far or where they are in the position. Okay, so for example, I have a link AB. AB is moving. I mean, it's a stationary picture, but it's rotating, right? So I have to have an angle or a variable that tells me where it is. There's theta, okay? Body BC is also moving and rotating, right? So I have to have an angle for that body, theta, okay? Body C is moving, right? So you see what I'm saying? Beta is changing, so I need to make sure that I know that. Beta is changing, okay? C is also moving, so I have to define a distance. So I'm going to call it YC, and if you notice, I'm measuring it from a fixed point. So here's a fixed point right here, right? Why did I choose that one? Because what I'm trying to do is make the geometry easy. I'm just going to draw this dotted line across here from point A, and I'm going to say there's a little spot right there, and it's fixed. And I'm going to define this distance here, YC, that goes from that fixed point down to point C. Okay? So that is the position of C. If you want the velocity of C, all you have to do is take the derivative of the position. The position is YC down. Right? That's the position. You can measure position from any fixed point. So if I'm measuring from that little red dot, the distance is YC, and it's down, so that's why it's a negative J, right? Oh, excuse me, it's the derivative of that guy, isn't it? Yep, shame on me. Okay, so position, so P for position is a negative YCJ. Now take a derivative, negative YC dot J. So that's your velocity. What's the acceleration? The acceleration is the second derivative. Okay, there you go. Those are the things I'm looking for. Okay, so what I've done is I've labeled angles for the bodies, and I've labeled lengths and distances for all of the moving points, right? Now, you know, B is moving, but it's on a body, so I'm not worried about that one. Okay, so here's what we do. What we're going to do is we're going to we're going to walk from A all the way around the mechanism. So I'm going to go from A over to B. So I'm going to go from here up to here. I'm going to go a distance in the horizontal. The distance in the horizontal is L cosine theta, and I'm going to go to the right. So that's a positive I. I have a vertical distance. It's L sine of theta, and then going up. That's why it's a positive j. So now I'm standing on B. I want to go to C. So I'm going to walk a distance L along the mechanism. That's what I mean by walk along the mechanism. I'm walking along the mechanism. I'm going to go a distance of L. Horizontally is going to be L sine beta. It's to the right, so it's a positive I. And I'm going down, right, a distance L cosine beta, and it's down, so it's negative j. Down is negative j. Now I'm standing at C. Okay, if I'm standing at C, I want to go back to A. I'm going to go a distance of YC. I'm going to go that distance. Which way am I going to go? I'm going to go up, positive j. Okay, so I go a distance YC up. Now I'm standing at that little red dot, and now I'm going to go a distance L, and I'm going to go left, negative I. When I get there, I'm back at the origin where I started, so I'm back at 0. So you set it equal to 0. Now, what you do with this equation is you always do this. You take two derivatives. If you want velocity, take one derivative. If you want velocity and acceleration, you take two derivatives. Okay? Here's the point. Don't try to do this. You can do it. It's humanly possible. But oh my goodness, you don't want to. Use Mathematica when you're taking your derivatives. The other thing to be careful of is, in this case, do not plug in the fact that theta is equal to 60. Don't do that before you take a derivative, because if you do, then you're not taking the derivative properly. You've got to leave everything as a variable until after you take your derivatives. Okay, what I'm showing here is, as an example, I'm going to take the first derivative by hand. So L is a constant. So this term here comes from the derivative of this term. Right? L is a constant. The derivative of cosine is a negative sine of theta. Don't forget the chain rule, theta dot. Right? I'm taking one derivative, so all of these terms better have one and only one dot in it. This one does. It's a theta dot. This term, does it have a theta dot? Yes, it's got a dot there. Does this term have a dot? Yes. Does this one have a dot? Yes. Does this one have a dot? Yes. So I think I did the chain rule properly. Okay, keep going. The derivative of the next term, it's L. Derivative of sine is the cosine times the chain rule. Take a derivative of the next term. L is a constant. Derivative of sine is the cosine of beta, beta dot. Derivative of the next one, derivative of cosine is minus sine, so minus minus gives you a plus. Sine of beta, beta dot. The YC is a variable, so it's plus YC dot. And this term LI, that's a constant, so it disappears. So when you're doing vector loops, a lot of times people don't worry about that. Okay, if you're doing it by hand, you extract two equations. Okay, so in the red line coming down, what you do is you pull out all of the i's. So here's a term that has an I. It comes from right here. That term there is this. Okay, this is not an I. Leave it alone for a minute. Here's an I, L sine beta. This is not an I. Leave it alone. Here's not an I. Here's an I minus L. So here's all of the i's for the first equation. Then you pull off all the j's. So here's a j term, right? Comes from this one. Here's a j term. It's coming from this one. Right? Don't forget one, right? And then this term is coming from here. Okay, so look at the red equations. Each loop equation gives you two regular non-vector equations. Okay, and from those, then, you can solve for two unknowns. What are the two things you don't know? I know theta, I don't know beta, and I don't know YC. So you could take these two equations and you could solve them for YC and beta. And I did it with Mathematica. You'll see what the answers are in a minute. And the beta will pop out magically. Boom, 30 degrees, which we talked about in the special points. So vector loops are really good for finding angles. They work great. And they work for everything. So you don't have to, you really don't have to remember all your high school geometry and whatnot. Okay, and now the blue guy is taking the derivative, and what do? You pull out all the i's. So I'm going to pull out the i's. Here's an I, which is right here. Okay, and then that's not an I, so leave it alone. Here's an I, so pull it out, L, cosine beta, beta dot. Okay, and that's all of them. And then you pull out the J's. Here's a J, which comes down to here. Here's a J, which comes down here, and then here's a J, comes down here. Okay. What are the unknowns in this one? Well, you could say beta's beta's not unknown. You solve the red equations for beta. You don't ever solve a one dot equation for a no dot term, right? You just don't, right? You get your no dots from the no dots, and one dots from the one dots. Okay. So what do you solve for? You solve for beta dot and y dot. That's what you solve for. How do you do the acceleration? You would take another derivative of this guy, another derivative of this, which is ugly, right? And then you pull off all the i's, set it equal to 0, pull off all the j's, set it equal to 0. What will you solve for? You will end up solving for beta double dot and y double dot. Okay? So I am not going to do the acceleration manually. Okay, so I'm going to pause and bring up Mathematica and show you that. Okay, what I have here on the left-hand side is the loop file before I added everything from the video, which maybe is a little easier. So anyway, here's the loop equation, the top black equation. On the right-hand side, I have Mathematica open. Again, just like before, these equations right here are all of this piece that comes from the vectors4.mb. Load it up and execute it so it knows I, J, K, etc. Okay, so now I'm using a loop. Okay, so just like before, I'm defining some simple vectors to kind of keep track of everything. I'm going to define an up AB. That's a vector that points up the AB link. And if you notice, I've got cosine of the angle theta horizontally, sine of theta vertically. Okay, hopefully that's no surprise. Then I have down the BC link. It's a horizontal of sine theta, cosine beta. Now if you notice, now I am making sure that Mathematica knows that theta is a variable and beta is a variable because I'm putting in this bracket T. So it knows those are variables. All right, the R from A to B is L up the AB. R from B to C is L down the BC. All right. So that with those definitions, now let's define the loop. The loop is equal to L up AB. I guess I could have used R8 to B, whatever. Okay, L up the AB plus L down the BC minus I, or Li, plus the YCJ. So that's what you have over on the left-hand side. Okay? That equals, it's an equation, so it's equal, and 0. And don't forget, it's a 0 vector, so it's 0 times I. Okay, the V loop, the velocity loop, is the first derivative, only one t here, first derivative of the loop. The A loop is the second derivative, see the two t's, second derivative of the loop. It's also the first derivative of the V loop. Okay, so you hit execute, here's the loop, not too bad. Here's the velocity loop, not too bad. And you can see that it matches what I did by hand. Remember, your ticks are dots. Okay. Here's the velocity, the acceleration. Oh my goodness, it goes on and on. You see, that's why you don't want to do this by hand. Right? But Mathematica, not a sweat. Okay. Now that I've finished all the derivatives, now I plug in the values. And I realize that the problem statement didn't say, but if you read the text, the theta was given to be 60 degrees. So you put in 60 degrees, theta dot, theta tick, that the author says call it W, right, omega. Theta tick tick, well, is 0. Why? Because W is a constant, right? W is a constant, so this guy's 0. Okay. Now what I'm going to do, since all the derivatives are taken, I'm going to do a vector solve. Like I said, you could probably just use solve. I'm going to solve the no dot, the loop equation. And what are you going to solve for? Well, if you look at it, the only thing that's up here that you don't know is you don't know the beta and you don't know the YC. Right? And so I'm going to solve for beta and YC. Remember, it's not YC, it's YC bracket T. So make sure you put the bracket T in there or it'll get confused and not know what to do. Okay. So here are the I'm going to shrink this guy down over here. Make it a little bigger. There we go. Okay, so here's full screen. All right, so you get this weird stuff, conditional expression. Well, the problem is that, well, not really a problem, but Mathematica tries to find all of the answers that exist. Well, when you're trying to find an angle, and let's say the angle is 30 degrees, well, 30 plus 360 is going to be an answer, and 30 plus 360 plus 360 is an answer, and that's what they're trying to tell you, right? So if you notice, they're saying it's pi over 6, which turns out to be 30 degrees, but it's pi over 6 radians plus 2 pi. What's 2 pi? That's 360 degrees times c. What the heck is c? C is an integer. Any integer is what c1 is. So what they're telling you is it's 30 degrees plus, and another solution is 30 plus 360. Another one is 30 plus 360 plus 360. So that's what they're trying to tell you. It's all the same. Okay. Oftentimes, you don't want all of the answers. Just give me one of them. And so here's what you can do. You can say, take the answer, temporarily substitute in for me that C1 is, that you get this by going minus and then greater than sign, and it'll turn into an arrow. And put a 0 in. Everywhere you see a C1, put a 0 in for me. Okay? So when it does it, it comes back with, it'll put the 0 in here, and so this would be pi over 6. And then this one is 5 pi over 6. If you notice, there's two answers. Right? There's two answers to this. The reason there's two answers is because there are two answers. Okay, so let me shrink this down. If you look at this guy, the beta, right, all it knows is that this value c is a horizontal length of L over. Well, the arm could be bent up. Let me draw it over here. Okay, the arm could be bent like this rather than, coming up and coming down to the length. It could have done this way and gotten bent up and it could have bent up and into the slot. That's the same thing as far as it knows. It's a different y, right? Each one has a different y. Each one has a different beta, but still this guy is in that vertical slot just like this one is. So the math doesn't know which one you want. So there are two answers, right? So if you notice, there's the two answers. Well, which one do you want? Well, what you can do is you can copy and just highlight this with your mouse, cut it, and paste it in. Or what I'm showing is a little bit more sophisticated. What I'm doing is I'm saying, take the C1, put it into the answer, and then parentheses. After you do that, give me the first solution. That's what the bracket, bracket, 1, bracket, bracket. It's weird. I didn't write it, but that's what you do. What this is saying is, give me the first solution. So if you notice, that's what it did. It gave me that YC is 0. That's the first solution. And beta is pi over 6. Beta is pi over 6. The second solution will be a negative y and 5 pi over 6. Okay? So I pulled off the first solution. There we go. So my answer is the first solution here. So I'm just cut it and paste it. That's the easiest thing to do. But if you want to be fancy, that's how you can be fancy. Okay. So now, I see that and I go, well, yeah, I don't like pi over 6. So here's another little gizmo. If you do divide, capital N, it'll give you everything as a number, right? So the pi over 6, it turns it into 0.5. But these are still radians. So if you convert that, you'll find out that's 30 degrees. So it'll tell you that beta is 30. That's what's nice about the roots. Okay, so now let's keep going. What I want to do is I want to solve for the velocity. So I'm going to solve the V-loop equation. What am I going to solve for? What you solve for up here? You solve for beta and y? Okay, you solve for beta dot and y dot. Okay, and then when you get that, you're going to have values of, well, okay, when you solve this, this is what you get. This is the solution of that. Notice that it has a beta in there. Where are you going to get that beta? You solve for beta. The beta was right here, right? You solve for beta out of the no dotted equation. If you also notice, there's a, there's no YC, it's a coincidence. But anyway, you have these undotted terms. Where do you get them? You don't get them from the dotted equation. You only get them from the no dot equation. So that's what I do here. I say, give me the velocity answer, the VANs, substitute in, right, divide, period, substitute in the answer. So take the no dotted answer and substitute those values into the velocity. So what it does is that everywhere it sees a beta, it's going to put in pi over 6. So it puts in pi over 6. Everywhere it sees a beta, here's another one. It'll put in pi over 6 there. Takes the secant, takes the tangent, does all this stuff, and here's your simple solution right there. Right? So the velocity is, the beta dot is omega. The YC is equal to negative L omega. Ah, why is that negative? Well, look at this, right? The velocity, well, head wrong. The velocity of this guy was a negative YCJ. YC is negative, so you have negative, negative J, right? So it's moving upward, right? The other way to look at it, maybe this is less confusing. YC is positive if it's down, okay? So if YC is getting bigger, then the block is moving down, all right? What is YC dot? YC dot is a negative number, right here. YC dot is a negative number. That means YC is getting smaller. If YC is getting smaller, then it's moving up. Okay, so it's moving up. All right. How do you get the acceleration? The acceleration, you solve the A loop for the double dots, right? Here you solve the one dot. The one dot, you solve for the double dots out of this one. Okay, so here's your beta double dot. Here's your YC double dot. That'll be the acceleration. Notice that there's a beta in there, right? There's a beta dot in there. There should be a Y dot. I think there's a Y dot. I don't know. But anyway, those come from the loop and the loop dot, right? So here's what I do. I take acceleration answer, substitute in for me the no dotted answer, and then substitute in for me the velocity answer. And then boom, this is what it simplifies to. You could do it by hand with your calculator also if you want to. Okay, just like a negative YC dot was going up, this guy is negative, he's also going up. If you remember, let me see if I can jog your memory. Okay, so you had this mechanism, went up like this, came down. We had a red dot, if you remember, there was a red dot right here, and we defined this as, this was C, this was YC. And we said the position of C was equal to a distance YC, and it was down from the red dot, right? That's the position measured from a fixed point. The velocity of C is equal to a minus, because it's there, the same minus, YC dot J. Okay, and we've discovered that YC dot is a negative number. Where are we? YC dot. YC dot. Yes, YC dot is a negative LW. Okay, so the velocity of C is equal to a minus YC dot is a negative WL. That is what I said. Right, minus from here. This minus is from the solution. Right here. Okay. So VC is equal to negative negative plus omega L J. He's going up. What's the acceleration of C? The acceleration of C is the derivative of velocity. The derivative of velocity is minus YC dot double dot minus YC double dot J. What's YC double dot? YC double dot is that. So AC is minus from here. YC double dot is minus L omega squared over the square root of 3 J. Minus minus is plus. he's accelerating upward as well. Okay, so hopefully that fixes the confusion on pluses and minuses. Okay, that's it. I'll post this as well. This is the vector root solution.